Okay, we've learned about electric fields and we've learned about the motion of charged particles in electric fields, and then we've learned about magnetic fields, and now we're going to learn about the motion of charged particles in magnetic fields. Let's get into it. So we've learnt that any moving charge creates a magnetic field, and we know that when two fields interact, we get a force. Basically, one object exerts a force on the other. So hopefully it'll come as no surprise that when we have a current carrying wire, which is obviously creating its own magnetic field, and we place that into another magnetic field, that wire will experience a force due to the interaction of the two magnetic fields. We'll explain that more in a sec. So, what do we need to know? Magnets, magnetic materials, moving charges, and current-carrying conductors experience a force in a magnetic field. It's almost a restatement of what I just said. The magnetic force on a moving charged particle depends on both the magnitude and direction of the velocity of the moving charge. We'll talk about that in a sec. The direction of the force on a current-carrying conductor or an individual charged particle moving at any angle theta to a uniform magnetic field depends on the direction of the magnetic field and the direction of charge movement. It almost seems those two statements say the same to me. So what do you need to be able to do? You need to be able to determine the direction of the force, the magnetic field, or the charge movement, given the direction of the other two. And we need to solve problems using these relationships here, which I'll talk about in a sec. So, firstly, if we have a wire, a conductor, and we've got a charge coming through it, and let's say this case here, that arrowhead means the current coming through the wire is coming straight out of the page. Remember, that's conventional current, which is the direction of positive charge movement. I might actually make a note of that up there. That is conventional current. Then, the way we work out that direction of the force is using the right-hand palm rule. And you can see from the diagram there, the thumb points in the direction of the charge movement. So in the case of this diagram here, the thumb is going to point straight up out of the page. The fingers point in the direction of the magnetic field. So in this case, the fingers point to the right. The force that the current or the wire, the conventional current, the positive charge direction, will experience will be out of the palm of the hand. So in this case here, the force would be directly up. Now, that applies for a current carrying wire, but it also applies for a charged particle, say here a negatively charged particle. This might be an electron moving through a magnetic field. Here, fingers point into the page, that's the direction of the magnetic field. The thumb shows the direction of movement of the charge, but in this case that's a negative charge and the thumb shows the positive charge. So rather than the force coming out of the palm of the hand, which would be upwards for a positive charge, the direction of the force will be the opposite, so it'll be out of the back of the hand, and so the force there would be downwards. So as it enters there, that force it would experience would be downward. Now that's going to cause the direction of the velocity, let's use blue for the velocity vector here, to change, and that's going to then mean the force will be like that. So what we're going to have, we'll talk about more of this in the next slide. The force is always going to be at 90 degrees to the direction of the velocity, which is basically going to set up circular motion, and we will get a path that looks something like that. That's not a great circle, but you get the idea, circular motion. So that's how we determine the direction. That's the first dot point here. How do we determine the magnitude of the force? Well, in the case of a current carrying wire, we use this relationship here. Force equals I L B sine theta, where B is the magnetic field strength. We talked about that in the last video. Has the units of Teslas. Strength. L is the length of the wire. Length. Try and write that a bit neater. L is the length in meters. That's in Teslas. Using up too much room there. And I is the current in amps. And sine theta is the angle of the wire to the magnetic field. So in this case here, let's use the yellow. If the wire went like that, that would be theta equals 0, so sine theta would equal 0. There's no force, so a wire that lays parallel to a magnetic field won't experience any force. If the wire lies at 90 degrees to the field, then sine theta equals 1. That will be the maximum force. And then for a charged particle moving through a magnetic field, instead of using basically IL, which is current times length, we use charge times velocity. Now, if you think about it, current times length is coulombs per second times by meters, and charge times velocity is coulombs meters per second. So it's really two different ways of saying the same thing. So force would equal QVB sine theta, where V is the velocity of the particle in meters per second, and Q, oops, changed my pen colour there, Q is equal to the charge, which will often be the charge of an electron, 1.6 times 10 to the minus 19 coulombs, or a proton, plus 1.6 times 10 to the minus 19 coulombs. So, you need to be able to solve problems with those two relationships. That is pretty straightforward, but I will go through an example on the next slide. So, previous exam question here. The diagram below shows a uniform magnetic field directed into the page. The magnitude of the magnetic field is 2.5 times 10 to the minus 2 Tesla. An electron travelling at a speed of 1.45 times 10 to the 6 meters per second in the plane of the page enters the magnetic field. On the diagram above, sketch the path taken by this electron in the magnetic field. So firstly, fingers are in the direction of the magnetic field, so they are downwards. Thumb is in the direction of the charge, but remember that's for a positive charge. So the direction won't be out of the palm of the hand, which would be for positive. Because it's negative, it'll be out of the back of the hand. So this electron will bend downwards. So the path will basically become circular like that. So we will get some circular path. Remember, once it leaves the magnetic field, not that it asks you, it just says draw in the magnetic field. Once it's left the magnetic field, it would go straight. But because it says just draw in the magnetic field, that's probably sufficient. We just need to show a circular path. It then says calculate the magnitude of the force acting on an electron. So we would go using that relationship we just talked about. F equals Q, and this is on your formula sheet, B sine theta, which it enters, it's perpendicular because it's in the plane of the page, and the magnetic field is directed into the page. So in a sense, that becomes force equals the charge on an electron. We can get that from the formula sheet. Times by the velocity, 1.45 times 10 to the 6, times by, I won't use the times sign there, times by 2.5 times 10 to the minus 2, times by sine of 90 degrees, which is equal to 1. If we plug all of that into our calculator, we should get, so all that equals, let me get the right colour pen, 5.8 times 10 to the minus 15 newtons. So, hopefully you can see that one, fairly straightforward process. Okay, let's keep moving. So we've already mentioned this, but let's explore this circular motion part in a little bit more detail. A charged particle moving at right angles to the uniform magnetic field experiences a force of a constant magnitude at right angles to the velocity. This force changes the direction but not the speed of the charged particle, and hence the particle undergoes uniform circular motion. That hopefully should be bringing back memories from the circular motion topic. Explain how the velocity dependence of the magnetic force on a charged particle causes the particle to move with uniform circular motion when it enters a uniform magnetic field at right angles. Basically, to do that, you basically say exactly what's written up there above. We'll talk about that. And then we need to derive this relationship for the radius of a charged particle moving through a magnetic field. So, first part, as I've already sort of said, this charge is entering. Remember, it's negative charge, so it's going to be downwards in this case here. So basically you are going to get a path that looks like that. Now remember, this is the direction of the velocity, so that at any point the force is going to be at 90 degrees, which is going to give you that circular motion. So basically, if you have a force, a constant force acting perpendicular to the velocity, it won't change the magnitude of the velocity, it'll only change the direction, hence it'll move in circular motion. Basically, exactly what's written in there is the sort of answer that you need to practice. It's the same as when we talk about a satellite and gravity always acting perpendicular to the direction of the velocity, or when we talk about the banking angle of a corner, the normal force, the horizontal component of the normal force, or the tension force in a string. All of those cause that. So that derivation is basically going to look like this. The force causing centripetal acceleration is the magnetic is the magnetic force. So that justifies what we're going to equate. So from that, we know that I'm just going to change colour here. F equals m times a. You probably don't need to do both of these. And a is equal to v squared on r for circular motion, so that we get F equals mv squared on r. And we combine those two, and we know here F is equal to qvb. We can ignore the sine theta because it says when it's perpendicular, so theta equals 90, so that therefore sine theta equals 1. So basically we can just forget that term. So we equate those two things and we get mv squared on r is equal to qvb. And then we rearrange that. We want to get that in terms of radius. So firstly, let's look at what cancels out here. The v there and that v there, because that's v times v and that's 1v, so that cancels out. And basically, to get it in the form that it's written, let's times both sides by r, so that and that cancels. And then let's divide both sides by qb. Whatever we do to one side, we've got to do the other. So q and q cancel, b and b cancel. And that leaves us with r equals mv on qb as required. So that's the derivation. We then need to solve problems with that formula. I won't go through an example of that, but that's fairly straightforward. It's similar to the sort of question we had before. Potentially we could go back to that question, and if we know the charge, which we did, we know the magnetic field, we know the velocity, and we know the mass of, say, an electron from a periodic from our equation sheet, then we can work out the radius of that charged particle in the magnetic field. Okay, let's keep moving, and I think we're almost about to talk about cyclotrons. So if you've watched the previous video on the motion of charged particles in electric fields, you'll see I skipped over the cyclotron stuff. I said we'll cover that now once we do magnetic fields as well. I probably should have almost copied that that stuff also into the science understanding from the SACE into here, but you can go back and look at that video in the notes if you need to see what you need to know. I think it'll be pretty evident once we get into it. So cyclotrons are particle accelerators. They're used to accelerate charged particles. Often they are protons or hydrogen ions to very high speeds so that we can collide them into another atom and make a new isotope. For example, at the they have a cyclotron in the Royal Adelaide Hospital they use for the PET scanner to produce fluorine 18. Is it fluorine 18 or fluorine 19? Oh, I can't remember. Anyway, a fluorine isotope that they use for PET scanning. So what is happening in that cyclotron? Firstly, we would enter a source of ions into the middle of this cyclotron here, somewhere like this. And let's say that's a positive ion, like a proton. And let's say we start off with this here would start off be the negative side, this would be the positive side. So that will get accelerated towards the negative side and it will build up some speed. Then it will enter the magnetic field. Now the magnetic field will act at perpendicular to the velocity, so it won't increase the velocity, but what it will do is it'll cause the direction to change. So that will cause this charged particle to go in a circular path and come back around here to this gap. So we call these two bits at the side, that's called the Ds. You can see it's got the D shape, and they are basically just two permanent magnets with a gap between them, and then we're applying a large voltage, a large potential difference between the two. However, what happens at this point, let's flick to yellow, is that this is an alternating power supply. So this gets flicked positive to negative, so it's the other way around. So when the positive particle reaches here, it gets accelerated across here, it gains some more velocity, and then it goes back into the magnetic field, and because it's moving faster, it'll have a larger radius, and it will come around here like this, and it will be ready to enter the magnetic field again. And you guessed it, the magnetic field will reverse again at this point, so it will get accelerated across this way, and then it'll go back into the magnetic field. It's moving a bit faster, so the radius will be even a bit bigger. It'll get to this point, it will have flipped, it'll go across here, it'll gain some more velocity or some more energy due to the electric field caused by the potential difference or the high voltage between those two Ds, back into the magnetic field, and it will go with an even more increasing radius. So I think you get the idea, hopefully now, of what's happening there. I won't go on and bore you any further. But that's essentially how a cyclotron works. So you need basically an alternating high voltage supply between the Ds and then a strong magnetic field inside the Ds to turn them around. So the high voltage accelerates them between the Ds and the magnetic field turns them around so they can go back through the high voltage again and again and again and gain more and more and more energy. So there's a couple of formulas we need to know. We need to be able to derive the formula for the period of rotation here. And what you'll see when we do this is this period does not depend on the velocity or the speed. And that's really good because basically it means you have a constant, the period is at a constant rate. So if you alternate the potential difference or the voltage at a constant rate, then you don't have to be changing the period all the time. So how do we work that formula out? How do we derive that? Well, we know that the velocity for an object moving in a circular motion is given by v equals 2 pi r over period. And we know that, the radius is equal to mv on qb. So if we rearrange this formula to get it in terms of v, we get v equals r q b over m. I'm hoping you can see how I've done that simple rearrangement. If not, go back to algebra school, please. So we can now equate those two things so that we get 2 pi r on period is equal to r q b on m. We can do a little bit of simplifying here. We've got an r there and an r there. And we want to get this in terms of period, so let's times both sides by period. Period over period cancels, that's equal to 1. Let's get rid of the m on the bottom here. Let's times both sides by m. Sorry, I'm taking you back to algebra school. See, I'm not as mean as you thought I was. And then we want to get rid of the QB here again. So we go QB there. We've got to do QB on this side. And the Q and the Q and the B there cancel. And overall, that leaves us with the period is equal to 2 pi m on QB. So there is that derivation. And as you can see now, as I said before, the voltage or the speed or any of that sort of thing don't affect the period. The only things that affect the period are the size of the charge. So if you've got uniform particles with the same charge and the same mass, and the strength of the magnetic field. So neither of those are changing as this moves through, like the charge stays the same of the particle, the magnetic field and the mass of the particle stay the same, so that you can have the period oscillating at a constant rate. The other formula we need to use is to work out the kinetic energy for a particle moving through a cyclotron. And let's change colour here and use green. And we know that from that formula just here that we rearranged, we know that the velocity is given by RQB on M, like just rearranging R equals MV on QB. And we know that the kinetic energy is equal to 1/2 mv squared. So if we substitute this into here, we get EK equals a half times M times RQB on M squared. And let's continue over here. So that all comes out to be EK equals a half M R squared Q squared B squared divided by M squared. We can simplify this a little bit. The M there cancels out that, if you like, M squared, because that's M and that's M times M. So we just get left with an M on the bottom. And I think that's as far as we can simplify. So we get left with EK equals R squared Q squared B squared on 2M. And let me just double check. Okay, I've written that in a slightly different order to they've got it there, but it is meaning exactly the same thing. So that's how we do those derivations related to the cyclotrons. We then need to be able to solve problems with those formulas. I haven't gone through an example. I won't go through an example problem in this video, but I don't think that should cause you too much distress. If you can understand what I've done there, plugging numbers into those formulas to solve problems should not cause too much trouble. Okay, that's it for the motion of charged particles in magnetic fields. Cheers.